on what we have discussed. Yeah, let me recap a bit on what we have discussed earlier, and then I'll just like come here. So basically, in the last session, we have discussed on what's big data, what's data engineering, and a little bit about the history of data industry in a very, very, very high level and nothing special. So basically, SQL started in around 1970s by one of the IBM researchers called F. Cord in 1980s and 1990s. RDBMS systems picked up. Oracle was one of the reason for it. And in 2000s, there was a lot of discussion on internet-based companies like Google, Facebook, Amazon, all of these companies to store large scale internet scale data sets. That's where the big data era started. Basically, they have created an ecosystem of tools called MapReduce, Hadoop file system, Yarn, Hive, Pig, Apache Spark. Later on, now we have cloud data warehouses like you know Databricks, born out of this Hadoop ecosystem here. So, and we have created Databricks out of it, and we have other proprietary slash open source data warehouses like Redshift, Snowflake, BigQuery, and ClickHouse. And we have others as well, but these are the main ones that I found most frequently referred in the market. So Google wanted to do internet scale data indexing for their web searches, or the Google search engine. So they had to create a system where they can store massive amounts of petabyte scale data sets, which can scale up, scale down as and when required. So that was the basis of what why we wanted a Hadoop ecosystem in the first place, right? So that was the need for Google. Since Google was a startup, they didn't have much resources with them. They did it with commodity hardware. We will see about that as well later on. And this is our basis of the whole big data era. I hope you guys can see it. This is acting up, man. I don't know why this tool is causing me a lot of issues. Mm, okay, so let me explain it. So they once they started off these projects, right? They prepared or they shared a lot of this data in huge in a huge manner. Basically, they created a lot of um, white papers and released it to the community. Whoever are interested, they built tools around it and they created an ecosystem of it. So they preferred open source era than commercial, software, which was present, but not really customizable or not flexible, or there was a lot of vendor lock-in and all of that. So open source basically cut short every of the nonsense, that was happening in the industry, and said, okay, we will create a pace of innovation that the world has never seen at a scale that world has never seen, and with so much flexibility that anybody can contribute here, and then create large scale data platforms that none of us has ever seen. So that's the whole motto of open source big data tools. And largely the systems which were handling the data, we could like categorize them into two things. One is operational one, which is OLTP systems, that is online transaction processing systems, where you have databases. Basically, you want to order an item on Flipkart or Amazon on sale. So there will be millions of users along with you who want to place an order along with you at the same time. So that's where these OLTP systems comes into picture. They are monolith systems. That means they have only one machine that is working for them, and they will just like um, operate on very small amount of updates, or updates at scale, like millions of updates, small updates, one or two row changes or one or two row creations, not more than that, at scale. So that is their specialty. So when we try to run any analytics query on it, they will not work because they are not designed for that. As simple as that, right? They work on each row by row. So that's not how we want analytics to happen. So okay, this is not working as expected. Give me a second. Mm, yeah, okay. So that's why OLTP systems, when Google wanted to like do a large scale, data ingestion and work on indexing the data, they fell short. Any database technology at that time. So what they did is they created a new system, new storage compute system, and we had OLTPs before as well, but they created a large scale system where they can process, store, process, and serve datasets that was never possible in the previous eras. So OLTP, on the other hand, which means they have a lot of resources, they can crunch lots of data, but they are not as fast as OLTPs, OLAP systems. Basically, these are online analytical processing systems where they crunch terabytes of data, and they provide some of the most complex analysis with slicing and dicing data. That means you can see same data in different ways, where you can query the data continuously and at scale. So they provide this flexibility, which OLTP systems never provided. So that's why they gained traction in early 2000s, because these internet companies were generating lots and lots of data. They don't know how to go about it, like how to generate value out of it. Let's say I want to check how many active users on my platform, or what is the year on year sales, what is the ad targeting that is happening. They have to crunch terabytes of data every day, right? Because the sites were very, very, very active across the world, right? And there was no restriction at all. Like, we cannot say that my, social media is working only from 8 a.m. to 10 p.m. That's not the case, right? It's working every day, every single hour, waking hour. So that means it generates a lot of data, it generates a lot of interactions. And we want to serve our customers or users as better as possible. So we need to collect the data, we need to crunch it. So how do we do that? So that's why these large scale data storage systems and processing systems came into picture, right? So now we will talk about data pipeline again. I just wanted to like give a precursor, data transformation, data pipeline, and data, engineering lifestyle I've discussed in the previous video. I'll not go through it. I just wanted to segue into our latest, topic here. That is, big data, and how we are storing the data. So the whole quote unquote big data happened when the internet companies started like really hammering our you know every single system with lots and lots of data. Because virtually, let's say, to be very frank, when the Facebook was, when the Facebook was at peak, right? Everybody we knew used Facebook, right? They uploaded photos, they uploaded videos, they tagged on locations, right? They wrote posts, okay, text, okay, they locations, chat, right? Real time chat. So all of this data is generated, at scale. Like, there were around 1 billion plus users on Facebook at that time, right? Imagine the amount of data that is being created at real time. If I am a business user, I want to know how many, a simple question like, monthly active users, sorry, MAU, right? Or DAU, daily active users. Who qualifies as monthly active users? Who qualifies as daily active users? Right? Are these people just logging in for 1 day in a month, or 5 days in a month, or just 1 hour in a day? How do you qualify that? This is a very, very, very huge, like, problem, not problem per se, problem statement, where you need lot of understanding of the data itself, as well as lot of data, because you have 1 billion plus users. How do you categorize those users in this segment? Even before we have to like create a segment, we have to store the data of 1 billion plus users, their profile data, their demographic data, and every data that they are generating every waking hour of their lives, right? So this is a problem at scale. This is not just with Facebook, this is with Amazon as well. Amazon has let's say, 500 million customers, right? Around the world. Imagine how many products we have to show on Amazon. Like, let's say we have 2 billion plus products on Amazon. I'm just giving a number. This is not true. Maybe it's more or maybe it's less, but I have to show my entire catalog to 500 million people across 200 plus countries every single waking hour of the day, and take their orders, process them, and track the order processing altogether along with the sellers, along with your inventory, along with your workers, along with your own business process and all of that. It's a massive amount of data. Like, you cannot imagine the amount of data that Amazon being generated every single hour. Okay, that is not just apps, that is website, that is apps, that is telemetry system, that is tracking, order tracking, location tracking. Every single thing is on Amazon. Google, right? That is basically like going to every single website on the internet and getting downloading the contents of the website and indexing it. It's a massive data. Netflix, right? It's a theater for the world, right? They have hundreds of thousands of paid users. Okay, I cannot imagine Netflix being down for less than a minute, right? And as soon as I like click on any movie or a series, right, I'll not wait more than a minute. Have to serve that. How does Netflix do that? How does they know about like how does they store movies? How does they store videos? How does they store all the telemetry that they are collecting from TVs, mobiles, iPads, laptops, PlayStations, all of these devices? You're understanding the problem, right? This is a massive, massive, massive amounts of data for each of these companies, right? These are the biggest companies in the whole wide world, and they have to solve this problem of big data. So how are they doing it? At least in the past, when the big data thing came into picture, all the data had three different distinct characteristics. That is volume. I have billion plus users. I am generating a lot of data, right? At at large, I have velocity. Like today I came to know about Facebook. Tomorrow, 10 of my friends came to know about Facebook. We 11 people created accounts and we started uploading pictures, uploading locations, uploading videos. So there is a lot of velocity that is being the data being generated at, and there is a lot of variety of data, right? Like you can see here, there is a lot of variety of data. This is not just for Facebook alone. This is true for every single company out there. So even simple questions like monthly active users or daily active users, it becomes a challenge to even like entertaining the idea of calculating them within like a day or within like a hour. So how do you store this data? Okay. Any doubts still here, or any questions basically? You need to talk, guys. Like, I'm sorry. Okay, cool. I take that as a no. So even like mission critical systems like banks, right? They generate like massive, massive data. Like, you cannot expect bank to be down, or a transaction greater than a taking greater than a minute. You will get scared, right? So, but at the end of the day, banks has to provide you services as well. How do they do it? They have to use your data, right? So this is a very, very, very important problem of our times, of our digital lives. So how do they do it? Earlier, when we had less data, they used to scale the database and called it a day. That is our monolith system. All our DBs, right? If we increase the resources, let's say I have 10 terabytes of hard drive, 128 GB of RAM, and 64 core CPU on this machine, right? This is my database. Let's say this is my Oracle database or a MySQL database, right? So, if it is a relational database, I'm just taking it for simplicity. I can, I can store this data when on the off hours, like bank, doesn't work after 5 p.m., right? I'll run my analytics queries and send it to my business, because business wants to see how many active users are present on my platform right now, or are they like, getting the right services or not. So suppose, I have like, uh, 10,000 users coming into new users coming into my platform every month, right? At some point, I will run out of the resources of this particular database. So how do I scale? I will take a bigger server that has double the capacity of all the things, and like, RAM, storage, RAM, and the compute capacity, and I will, transfer all of my data here. And I'll say, okay, this works for some time. So the amount of performance that you get out of these two systems will be roughly equal to 2x, because we have resource increased the resources 2x. This is how it will work. But after some point, there will be something called as law of diminishing returns, right? So diminishing returns meaning, right, you increase the day, right, you increase your resources twice, okay, but the amount of performance that you get is around 1x, not 2x, because even though you are increasing the resources, right, your process can only get so much faster. It will not get 2x faster, even though you are increasing 2x or 3x or whatever it is. That is how these systems behave. This is called horizontal scaling, right? Sorry, this is called as vertical scaling, not horizontal scaling. This is vertical scaling. That means you are increasing the resources this way, right? This is vertical scaling. My bad. So you can only increase amount of resources and performance to a certain level, and you will plateau something like this curve, right? This is how it works in like vertical scaling. Now, this is not suitable for our needs where we calculate like, something like monthly active users or daily active users or some metrics, right? Because we have to take the user request that is coming in 24/7, and we have to query our database at the same time, which can cause downtime for our databases, because obviously, like, databases are not, our operational systems are not suitable for these kind of complex querying or analysis. Basically, they are good at like, taking transactions, and like millions of transactions at a 1 second, and then executing them at scale. They are very good at that, but not at analysis. So now engineers around in when internet happened and these internet companies were trying to figure out how to do it, they came up with distributed systems. There were distributed systems earlier, but they created an architecture where we can add same amount of replica. Let's say I have this one resources one, like some amount of uh, RAM, some amount of storage, and some amount of cores for one master and workers. I can coordinate between using a node, master node. I can coordinate between all of these workers and distribute my storage and processing as well, so that I can increase whenever I need, I can increase whenever I don't need, I can decrease, right? Increase as well as decrease as and when I want, using this one, so that I can scale my system as and when I want, scale up and scale down, right? This is basically our OLAP systems, or online analytical processing systems, which are distributed in nature. Okay, this is basically the you know right. These are this is basically an argument for distributed system. They scale horizontally. This is called horizontal scaling. Okay, right. This is vertical scaling, where you increase the resources of single machine. This is like adding new machines which have same resources in the cluster. Suppose this is resource one. Okay, these are all resource one of type resource one, right? Suppose I want, I'm seeing that my cluster is almost full. I have 200 terabyte of cluster, overall cluster storage across, spread across three machines. I don't have any uh, space left. So I'll add one more, plus this is around what 33 terabyte of storage in this machine. So I get 233 terabytes, right? This is how it worked in big data era. It still does.
One quick question, Money.
Yeah, go ahead, Shashi.
Money
Yeah.
in horizontal or in vertical,
Hmm.
in any way we are increasing the capacity of the system, right? So
Right.
I have recently attended Azure Fundamentals certification. There are
Okay.
questions regarding horizontal or vertical scaling.
Right.
So how do we determine, like you are saying, we are adding more virtual machines, and
Right.
in another way we are adding more storage. How
Right.
to? I mean, this is a confusing concept for me. How to
Okay.
put it into vertical bucket or horizontal bucket? Can you give
Right.
a simpler version?
Right. So my rule of thumb is if you are, you know, like handling a mission critical system like a database where you have to quickly update your resources to match the performance characteristics that you need and less with less complexity. Okay. Okay. Let me be very clear. Your database is a very mission critical system, right? And to increase the like capacity of that in horizontal scale, sorry, in vertical scaling, it is very easy because you don't have to change any logic, right? You have to like migrate your system at some point, but what you will do is you will just create the snapshot of this machine first, and then put that snapshot into a bigger machine, and you will start accepting request onto this machine. Okay, this is your vertical scaling. Doesn't have to
Okay.
require many this one, but okay, this is one way of scaling, right? This is mission critical system. You don't want to mess with your operations because your once your users loses trust because your system is down for a lot of time, so it will not work. In distributed system, it is very easy to add resources, but it is very like very complex to maintain that system in terms of how do you say that my data is consistent among all the machines. I'll explain why I'm getting this point. This is a very hard problem in whole computing industry. Okay, not just this system, their data or not. This is a very hard problem. Like you don't want this complexity unless you want this complexity from day one. Let's say for Google, it is not a choice, man. It is not a choice. They will use like lot of sophisticated techniques that will like entertain monoliths as far they they can take it as far as they can. But if they had to like migrate to a distributed system again, it causes a lot of headache to them rather than a easy solution or easy migration. So they'll have to do a lot of gymnastics, right, around that one, mental gymnastics and organizational gymnastics. So they will certainly opt for a distributed system from day one because their scale will be massive, right, to begin with. But for normal users, right, having a database system and running analytics queries on it, which if you have couple of thousand users and or even a million users, right, running analytics queries on a downtime when there is not lot much of traffic that is going on here, just by increasing the resources of that particular system is fine. But you have a requirement to store massive amounts of data and scale it accordingly on the future anticipation, right? Then that is where distributed systems are used and scaled. You have to understand the use case first. You cannot think that we have to scale it vertically or horizontally. You have to understand the case where why do you need distributed systems in the first place. You need distributed systems in the first place so that you have the use case. Like you are storing hundreds of terabytes of data and you don't want that system to be having any downtimes, and you want to maintain the system as easily as possible because it takes a lot of expertise to maintain the system. These are not cheap or easy systems to maintain anytime because you are running similar whatever you are seeing the specs here, you are running on one box each. That means you are paying the cost of six boxes or five boxes instead of paying one box here. And to maintain the data consistently across these boxes, right, it's a huge challenge. We will see how this is mitigated in our data side in Hadoop clusters and all of that. But it's a huge challenge in and on itself. So we are finding the use case where we want to fit in that data. Am I clear here? Cool. Hey Shashi, am I clear? Okay. Give me a thumbs up. Okay. So coming to little history on why we need HDFS and where it came from. So when all of these challenges are being faced in the industry and everybody is trying to find the next best thing for storing large scale data sets and processing at scale and generating value and becoming the best company known for their whatever they are doing, like Google being the internet search engine, Amazon being the internet e-commerce, and Netflix being the internet's theater, and Facebook being the internet's internet social network basically. So when these companies are actively working, these are guys from PhDs, these are guys from like uh, very 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 good, having great technical knowledge. They all like doing some effort in here, but the biggest one that came from is a project called Apache Nutch, which was created by Doug Cutting and Mike Caffarella. So these guys, created something called as Apache Nutch, which later became something called as Hadoop ecosystem. And what they did is they said that, okay, we are going to, create a distributed file system that we discussed here. And they actively said that, okay, we want to create a distributed system where we have one master and worker nodes, where we scale the storage as well as compute as and when we want. Similarly, what Google did is in 2003 they released a paper. I told right at that time everybody was exploring the field and contributing through releasing white papers. So they said
Hi, is the connection lost or is it for only me? Hello?
okay, what happened? Can you guys hear me?
Yeah, now we can. You were frozen a minute ago. Yeah,
Okay, I think there was some internet interruption, man. This is really bad. Can you guys see my screen?
yeah, now.
Okay. So yeah, I was talking about Google, right? Were you able to hear that?
Yeah, in 2003, Google introduced a
Yeah.
paper. That's
Okay.
where we had.
Yeah, yeah, yeah. So basically, what these guys said is, like there was no ads at that time. There was no revenue generating thing at that time. Like they want to store, like create a internet scale, data sets where they want to like index the data and create a search engine, right? That was their, Google was created by Sergey Brin and Larry Page. They had this idea in their PhDs, so they were working on this problem for a long, long time. So they had to be very inventive. What they have done is we will create a file system where it scales well, but instead of using state of the art, very specialized servers, we will do it on commodity hardware. Okay, which means that I can report any data where desktop. I can find the core, the motherboard, the RAM, the hard disk on it, and hook it up on a network and create a cluster of machines like the one that we saw here, right? Like the one that we saw here. I want to create this and see if it scales well, and we can do the internet indexing for our search engine. They were succeeded. They succeeded. That's what you are seeing here right now. This is the first cluster working cluster that Google has created. This is in Museum of San Francisco. Google has donated this one to Google, like Museum of San Francisco, and it is still there for viewing basically. So it's a, they said that, okay, these are all desktops, by the way. These are all normal desktops. Okay. They hooked it up with network and they created a cluster, basically. Okay. This is not new. There were a lot of companies that did that, but not on commodity hardware. What happens, with commodity hardware is they fail. They fail all the time, right? Under massive loads, under normal circumstances, they just fail. That's it. Internet connectivity not happening, they fail. Their tasks will fail, right? The idea is to create a framework, to create like a software which can handle the failures of commodity hardware, both hardware wise, both software wise, and both just power outages or anything. They wanted to create a massive storage system that could handle failures of these, of any kind, basically, unless there is like complete area wide power outage or anything like that, right? They wanted to handle all of this. That is when they released this white paper and saying that, okay, we have created this massive file system called Google File System. We are internally using it. We are running jobs on it. We are processing data on it using our processing framework, which they didn't reveal yet. And then they said, okay, we can scale this up to certain terabytes and without any issues. That's what they said. Everybody started working on that project, and they created something called Hadoop file system later on, again by these guys called Doug Cutting and Mike Raffaella. Hadoop is the word that Doug Cutting's son gave it to his pet elephant. That is why you see Hadoop ka logo as an elephant. So Hadoop is a made up word. It was not a word at all in English language or any language for that matter. So this is the trivia I wanted to tell. So this is the first ever Hadoop cluster or distributed cluster that was used with commodity hardware and for data processing. Okay, you can see Larry Page and Sergey Brin's faces here. So this was the challenge that Google, since Google was a startup, they didn't had funding. They wanted to like create a they were inventive at that time, like really inventive, because they hired massive PhD guys. They had best of the best from the industry for a startup. So they had to come up with these kind of stuff. So web scale means like massive data that's present on all of the internet, basically, right? So how do we do that? So that's where we are discussing now. So before we say, go into Hadoop file system architecture, I just want to stop for a minute and say, are you guys following me till now, or is there anything that I need to revisit here? Anyone, just give a thumbs up or thumbs down. Thumbs down means you're not following me.
Oh,
Thumbs
yeah,
up
good.
means,
We are good, money.
oh, cool. Thanks for the feedback, guys. Yeah. So now, so let's not go into a Hadoop right now. Okay, we will take about one example. Okay, where we have a file on our system on our laptop. Let's see how it is stored on a hard disk drive. That means a magnetic hard disk drive. This is a magnetic one, right? Where you might have had this hard drives where it used to spin and make sounds in our laptops, right? Nowadays it's all SSDs, but this is where the data was stored previously. When Hadoop came into picture, right, all we had was magnetic disk drives. Okay, why it is important, I'll tell you later on. Okay, SSDs were very expensive. They were not invented properly yet, and even though they had some SSDs, the capacity was very low, and they were very like too much too much costly, like millions of dollars for a gigabyte, something around like that. At least $100,000 for a gigabyte or two, I believe. That was the like cost at that time. So right, everybody used hard drives because they were cheap and like that. So when you want to store some data like a hard disk drive, like 500 MB, right? So your hard disk drive, is a magnetic drive, right? So this is a circle basically. So every circle has a sector, right? In just normal mathematics, sector means a pie, like a piece of this pie, right? Every time your data has to be stored or retrieved, the hard disk drive has a needle on top of it, and it has to literally spin the disk, in clockwise or in anti-clockwise. Okay, and point to that portion on this one and read it from here. Okay, even today, right? This is the case. So suppose I have stored a movie that is in this sector, right? So my hard disk pointer here that I've represented here, right? It has to literally, if it was here reading this file, if I requested a movie later on, it has to literally come here and request, read the data from here and pass it on to my RAM, and my RAM will put it onto my CPU. CPU first, sorry, loads into RAM, and it will show again, CPU will push it to my screen. So that's how it is. Okay, this is the basics. Okay, so every single time it starts to read or write, it can write up to 512 bytes at once. Your 512 MB file will be divided by 512 bytes in each, right? It will be made into 512 bytes. Okay, why? Because that is the highest amount that this hard disk can read at once or write at once. Are you guys following me? Yes,
Yeah.
no? Cool. Awesome. So after some point, they decided 512 bytes is very low and it's taking a lot of time. So they have increased to 4 KB. So that is the this one. This is all about magnetic disks. Now we have SSDs where we have page sizes and blocks. Okay. So they have 4 KB, 8 KB, 16 KB page sizes, and each block, this is a page. Okay, this is a page, and this is a block. This whole thing is a block, right? So this block is 128 pages basically. That's how it is. That's how your data is arranged on an SSD. So every time your file has to be read, it will be read in these blocks of memory spaces on your disk. Okay, am I making sense? Okay, I'll take that as a yes. So now, why am I saying all of this data? So in Hadoop file system, this is a distributed file system, right? That means your data is spread across all of these worker nodes, okay? Where your file will be like broken into chunks, and it will be these chunks, each individual chunks will be stored in one worker machine, right? No two same chunks, like this chunk will be present in this one. Okay, one worker. I'll tell you what it means and why we are doing it. Let's say we have 500 MB, right? 500 MB file. So our Hadoop cluster will divide this into 128 MB megabytes in one block. This is one block. Okay, why? Why does it like create 128 MB blocks? Any idea? Or why do we have to create blocks in the first place? Come on, guys. Just throw something at me. No worries. Because we want to store data in a distributed system and we don't want to lose the data in the first place. Suppose I've stored all the whole file here, right? And this worker node goes down. My data is gone, right? So we want to make sure that the data is stored in a way that even if I lose some nodes in the cluster at any given point, I can get the data from other remaining clusters and recreate the data and create a new node basically here and refill the data from other nodes. Am I making sense? Okay, I see the silence. Okay. Now, so since your hard disk is and your SSDs are reading the data in pages and in blocks at once, your Hadoop cluster also does the same thing. Okay. So every file that you input here, it will be broken into chunks. If it is less than 128 MB, the whole file will be stored in one machines, and every data that you store will be stored, you know, 3 copies at least. You can configure this in your cluster, but at minimum, it will store 3 copies so that your data will never be lost. Okay. So why do we need to store data in 3 copies? Because of the data redundancy that we need so that we don't lose the data. The idea here is that since we are using commodity hardware here, we expect that there will be machine failures down the line, right? And we are anticipating it. Hadoop cluster guarantees that even if your files are stored across different machines and one of the node goes down, I can replicate the data from other nodes because I am storing 3 copies here. Okay. So how does this do? How does this store the data? Is it just only uh, like just we have a file and then it is just dumping the data here? No, it's not happening like that. How it will store data is in the Hadoop file system, there will be one master node which will hold the metadata and the like the this one the like it will maintain all these nodes and it will maintain the metadata of what data is stored where on which node, which data is stored. All of this will be maintained by master. So let me give you a very normal example, right? Suppose you are organizing a event, okay, and it is on you to see that every single aspect of your event goes well, fine. So you are arranging like a lot of different activities. Let's say a birthday party, right? Where you have to bring in food, you have to bring in, arrangement for the guests. You have to do all sorts of things for, different people, be it for kids, be it for, adults, be it for the birthday and whoever is celebrating the birthday, right? You cannot do it on alone. You have to need one coordinator and, 3 or 4 people who can work along with them. So this coordinator will have the contact details of each of the workers or each of the subordinates who are working with them, and they will know when to call them and give them, assign the tasks and get the updates from them, right? So imagine that is your Hadoop cluster. Let's say tomorrow you are doing a birthday party, you hire 4 people and you are trying to like coordinate the tasks between them and give the tasks between them, give some data points to them, or a checklist as to what they should do, and you give them some time and give them some resources, and they will update you that progress of the task from time to time as and when you ask them, is it happening fine, is it do you need anything else? So this is the functionality of a Hadoop master or Hadoop name node. Basically, this is called as a name node and this is called as a worker node. Okay, this is called as a worker node. So why do you need this complex arrangement? Because I cannot do all the stuff on my own, right? Am I? No, even if I'm a Superman, I'll miss a lot of things. So I need some people working on my behalf and on my command. So this is how an Hadoop cluster is designed in the first place. So suppose I want to store some data. I already said that, we are going to make the data into blocks, because as I mentioned, Hadoop file system is a block storage. Everything that we store on Hadoop will be a block in blocks. Whereas something like AWS S3 or Azure storage or Google file system, these are all object storages. I'll discuss about this after we discuss about Hadoop at length. But yeah, these are object storage. They will store files as is in one server, and when we access the file, we will just access the file all together at once. But that is not how it is designed in Hadoop cluster. So what it allows is that even if the data is increasing every single day, I can just add one more one more worker here, and scale my storage to a point where I can accommodate the storage of this data. All good? Thumbs up, guys, or thumbs down. Okay. So now this is how the Hadoop cluster stores the data. So how does this manage it? Like, how does this master node knows where my data is? Let's say I am sending it a query saying that select star from so and so table. How does the table data is stored here? Or I want to access some file in the Hadoop cluster directly. Let's say I'll say ls and so and so folder name. So directly I want to do an ls list or show the contents of a folder on a Hadoop cluster, just like I do on a Linux box. So how does this work here? So I'll explain that. By the way, these are all normal Linux machines, right? These are all Linux machines. Whatever the commands that you worked on Linux, like ls, move, move, copy, all of these commands work here as well, but in a slightly different way. Okay, but they certainly work. So Hadoop system is a POSIX compliant system. That means you can work it as a proper file system like this. These are all POSIX commands. Okay, POSIX commands. We call them as POSIX commands. Just put this in your head. You don't have to worry about it. I'll explain what it means later on. Right. So this name node is the master or the coordinator or the orchestrator of everything that is going on here. So what does the name nodes capabilities are like? Name nodes capabilities are like, first things first, it has to connect to these nodes, worker nodes, anywhere. So it will have the IP addresses of each of these nodes, basically the IPs of each of worker nodes present in some config file here, and then the connectivity here. So that is one thing. Okay, worker node connectivity name okay, I'll write name node. Okay, worker node connectivity. Okay, and we will also check this one, liveliness of the nodes. What do I mean by liveliness? Right, of nodes. Suppose I have connected it. I told, right, this is a commodity hardware. That means sometimes it will just erratically, if I'm running a query or if I'm trying to access the data on this cluster, so it can take a lot of time. How does this name node, master node can assure that we are getting the right data at the right time and the node is not down? So it will constantly ping this particular name node and every single name node on the cluster every 5 minutes and check, okay, are you alive? Are you alive? Are you alive? So it will constantly ping that every 5 minutes or 1 minute. We can configure this on the name node to check what is the interval. And if that interval passes and then this worker node didn't give any signal back, 3 times or 2 times, right? It will kill off this node. It will take the data that is present in all of the other nodes and it will just, replicate a new node here. It will just replicate a new node here. So that's how it works, right? So this is one. The next thing is about the data. So name node or master node will also have the metadata of what data lies where. All the blocks that you are seeing here will have, let's say this is block one of the file one, right? This is block two. This is block three. This is block four, right? A name node will have a massive data, right? Massive table saying that, okay, this is block. Okay, this is my IP of the machine, worker machine, and this is my, location on this machine, right? Where my block is stored. So like that, there will be metadata table. This is a massive, massive metadata table because we'll have a massive data that is stored on this one. So for block one, I have worker one, I have in this location, that is folder one, right? So likewise, block two, block three, right? Worker two, worker three, right? Same thing, folder, folder. So it will create a metadata like this, and it will, the name node will have this metadata table here, right? So it will check the worker connectivity, it will check the liveliness of the nodes, it will, have the metadata of the nodes. And even, it goes to a point where the every single hour or every 30 minutes or every 10 minutes, the name node also asks the worker nodes about whether your blocks are corrupted or not, whether this is called as block report. Okay. The worker node has to provide a report as to what blocks are corrupted and what blocks are fine. Okay. If the block is corrupted again, it will be discarded here and the other copy will be present here, right? Block one in different node, right? This is block three, this is block two, like that, right? It will be stored here. So these blocks again will be transferred here. Let's say block one will be transferred to this machine. So that's why it needs a block report. So these are all the things that a name node does to store the data, to scale the data, and to maintain the integrity of the data. Suppose you have stored this data, right? And the data is corrupted. It doesn't have any value, right? So the name node ensures that your data is very, very, very much intact and it is ready for, running any queries. So that's how this Hadoop architecture works, or Hadoop file system works. Any doubts? Okay, I see thumbs up from Kranti. That's great. So there are other stuff here as well, but I know we will discuss in next step. So now you understand where I made the connection, right? Like, we have a file, normal file, and when we are storing on the disk on our own laptop, on our own hardware, right? It will be stored in blocks, like small chunks of data that the computer that the CPU can read at once in blocks, right? It cannot read one byte by byte, byte by byte. So it will store clusters of data of our files, and then when we have to read, we will read each and every sector at once in a block, in one sector at once. And if this block different block is at different sector, our hard drive, like the pointer in our mechanical hard drive will point here and then it will read. So similar thing will happen on magnetic SSDs as well. Same thing will happen in Hadoop cluster as well. But here the size of the like each block will be much higher because we are storing lots and lots of data, right? Terabytes, petabytes of data. If we have, simple blocks like, 5 bytes or, even a megabyte, the amount of metadata generated here will be massive, right? Like even a, 1 GB file will have like what, 100,000 blocks or, a million blocks, right? If you have, one byte of, 1 byte or 4 kilobytes of, block sizes. That's why we have, 128 MB of block sizes, right? So when we are storing that in our, worker nodes, we will try to, create metadata for these tables. If the block size is too high, we cannot read at once, it will be slow. Our operations will be slow. If it is too slow, name node cannot handle the metadata. So the Hadoop guys who have created these systems and worked on for years, they have seen the performance of the system. At first, it was actually only 64 MB, right? And then they increased to 512 MB and the block size, I mean, 512 MB, and they saw the performance dip massively, and they settled in between these two, which is 128 MB. Right? This is an empirical one. This is not a scientific one. This is trial and error. Empirical means basically trial and error, right? So they have come up with this one. Data corruption is less, performance is high comparatively, and even the name node is not stressed. They have seen all of this, empirical data across, companies like Facebook, Google, Amazon, and they contributed to open source projects afterwards, maintaining these clusters, massive petabyte scale data sets. So this is how these distributed system works in theory. In practice, it will be very different, but in theory, this is how it works. Okay, so I want to get some feedback. Am I doing wrong? Sorry, am I doing right, or is there anything that I might have skipped, or are you guys feeling fine here? Please let me know. I'll just move to next topic. Meanwhile, thumbs up, guys. Thumbs up or thumbs down. Basically, I'm not forcing you to thumbs up, but yeah. Okay, cool. So now we'll discuss about Hadoop, file system properties. So it is a distributed one because our storage is distributed across different machines here, and we have block storage. Our files are stored in block. It is fault tolerant because it has redundant copies of the same data stored across different workers on the same cluster, and it is highly scalable. We can just add nodes, and it it follows a convention called worm model. What do I mean by that? That is write once and read many times. Okay, why is that? Because we are using this data for analytics, we should not have any access to modify the data in the first place. Even if we want to modify the data, it has to follow certain pattern. We will discuss that later on. But we should not be modifying the data, because if somebody modifies the data and manipulates it, then trust on the system is basically zero, right? Like I cannot trust the data on the Hadoop cluster. I cannot trust on the numbers that is generated by whatever is stored on this data, Hadoop cluster or on this system basically. So business user comes and says, I'm not trusting you because I don't know, maybe you might, the data might have been corrupted or you might have manipulated the numbers, right? They obviously can say it. So that's why to eliminate all of these confusions, they created this convention called write once and read many times, right? So this, what it means is that your Hadoop cluster is a distributed monolith. That means we refer to this cluster as a single unit. That is why we are calling it. And internally, it is a distributed system. This is a distributed system, but we refer to this as one single entity. This is one single entity. Okay, right. So this is called as a distributed monolith. Okay. The old databases that I spoke, that is monolith. That is the pure monolith. This is a distributed monolith. So whatever I'm putting the data in from my operational systems or my databases, operational system, SYSTEMS, or OLTP systems, I need that copy as is. I need that copy as is here because I want to run queries again and again and to check whether the my analysis is correct or not. If I change the data here anytime, gone. My trust and what I have done 10 months ago or 5 years ago, I don't remember, right? My, if I want to recalculate anything, that cannot happen. So that's why to avoid all of these confusions, they said, okay, I'll create a distributed monolith. I'll, try to think of it as a database which stores my data on different machines. And there is a coordinator here. So what it will do is I'll try to write only once in the data at a certain part. And I can read it many number of times. I can create any number of data sets from it. It doesn't matter for me because I can just scale up these data sets. If I want to have massive data sets created out of raw data, I can just add more nodes here and then it will be fine, right? But I don't want to mess with the data that is coming in from my operational systems because I want to establish a trust on the system, right? So this is the model that they have followed. There are many drawbacks on this model, which we will discuss in the next section. But next, session, I will try to conduct it in next week, but in the weekend itself. But yeah, so this is how we created the Hadoop file system. We will go into much depth coming in the coming sessions, but I hope you guys had a good understanding of what we discussed on this one. Any doubts? This is for the last time we will discuss about doubts on this session, and post that I will just stop the recording and we can discuss for a couple of minutes and then we can disband.
All good morning. Yeah.
Yeah, Kranti, go ahead, please.
I'm just saying all good. Yeah.
Oh, all good. Okay, cool. I think I'm going to stop the recording now. It's been, yeah, it's been an hour. So, where do I stop? Yeah.